Hey again, today we're going to be talking about forward and reverse reactions and reaction mechanisms. So let's get started. Anyways, so some reactions can go forward and can go backwards. So here is a example of some reactants and some products. Now the reaction can go forward like this. So the reactants combine and then they make products, but at the same time too, the products can decompose and they can make reactants. So as in some reactions, as a forward reaction is going forward, the products are turning into reactants, and then the reactants are turning into products, and it keeps going into this circle, and you'll always have reactants and products, and you'll have some kind of balance, or sometimes what we refer to as a equilibrium, which we'll talk about a little bit later. So again, some reactions can have a forward reaction and some reactions can have a reverse reaction. So how does that relate to our potential energy diagrams? Well, let's take a look here. So here's an endothermic reaction, and we have the EAF. Now, as we remember, EA stands for activation energy, and F is just going to stand for forward. So the activation energy for the forward reaction, and right here we have the activation energy for the reverse reaction. And then delta H, which we've already covered, is the change in enthalpy. So the forward reaction here, the amount of energy for the forward reaction to occur is right here. So A right here is our EAF. So here is our EAF. Our activation energy in the forward reaction, our EAF, is A. Now, so that's how it's going to go from reactants to products. It needs to go up by this amount of energy. This is the amount of energy it needs for it to go forward. Now, how much energy does it need to go from products to reactants? Well, it needs to go up by this amount of energy, which is labeled B. Okay? So this is our EAR, our activation energy in the reverse reaction. So from products, it needs to just to go this high to reach the reactants. Okay, reactants need to go this high, much higher, to get to products. So it takes less of an energy increase for products to become reactants. It takes a very large energy increase for reactants to become products. Now, delta H, as we know, our delta H is given by this formula. Our H of the products minus our H of the reactants. So our delta H is going to be right here, which is about 300, and our H of the reactants is about 100. So our delta H is going to equal 300, okay, the potential energy of the products, minus 100, and therefore our delta H equals 200, positive 200. So right here is our delta H, which equals 200, and whatever this unit is, which is probably kilojoules. Now, as we see here, our EAF, our forward activation energy, is equal to the delta H plus EAR. So it's delta H, this plus this equals this. And we can clearly see that here plus here equals delta A, or sorry, EAF, the activation energy of the forward reaction. So let's look at an endothermic reaction. So again, we have the activation energy in the forward. So this is our reactants, and C and D are our products. So the amount of energy for it to go from reactants to products, it needs to go from reactants to products, and it needs to go up by this amount of energy. Okay, so this is what we call our EAF, our EAF. And from products to go to reactants, it needs to go up this amount of energy. So much higher for an endothermic reaction, but in the reverse, it's going to be, or sorry, the reverse is endothermic. This is a bit of a mistake right here, and this should be exothermic reaction. So, and as you see, this would be our EAR. Now, what we see here again is delta H equals HP minus HR. Okay? Or in other words, this distance is our delta H. Okay? Or in other words, our delta H equals HP of our products is 20 minus of our reactants is 40. Delta H equals minus 20. Okay? Now, as we mentioned before, our EAF is equal to EAR plus delta H. Now let's plug in some numbers here to figure some things out. So EAF, well, we can calculate that, but is equal to, now what I'm saying is this number plus this number equals this number, and that doesn't seem really right. But if we plug in these numbers, we see EAR, which is 20 to about 100, so this is 80, and we're adding it to minus 20. Now it starts to make sense. And that equals our EAF, which is 40 to 100, which is 60. And that's right. So you can use the same formula right here for an endothermic reaction or an exothermic reaction. Now we're going to look at some reaction mechanisms. So the reaction mechanism is the actual sequence of steps that happens during a reaction. So a reaction, it normally happens in just a few different steps for a number of reasons. The number of reasons is, well, mainly probability, and we'll talk a little bit about that later. And probability just means the chances of molecules hitting each other. But reaction mechanisms just means that reactions happen in maybe 2, 3, or 4 steps. So here we have a reaction that is happening in 3 steps. So this would be our step 1. Oop. This would be our step 1 right here. Step 2. And step 3. Okay, so step 1, 2, and 3. And what we see is that after these steps happen, then that is the total reaction. So what a total reaction is when you just add all of these steps up together. So what we did is we just added all these steps up. So 2NO, N2O2, we added these 2 hydrogens together to get 2H2 and right here, N2O right here. Then we add everything on this side together. So we have 2 waters, we add 2 waters, 1 nitrogen is over here, 1 N2O, which is right here, and N2O2, which is right there. We just added everything up. But then what we start to see is that some things can start to cancel out. Like this N2O, and this N2O, and this N2O2, and this N2O2. You can start canceling some of that stuff out. And if we do that, what we see is if we cancel N2O with N2O, it cancels out. This N2O2 cancels out with this one. And then what we're left with is 2NO plus 2 hydrogens, and make N2 plus 2 waters. So what we did was we canceled out this, and this, and this, and this. And what we're left with is a net reaction. Okay, so again, what we canceled out is here and here, and here and here. So, or in other words, we canceled out this one, and this one, and N2O, and dinitrogen monoxide. And we're left with 2NO, 2H2, 2H2O, and an N2. And this is what we call our net reaction. This is the reaction that you normally see as a net reaction.